In this lesson, we're going to talk about how to solve a system of equations using the substitution method. Let's go ahead and take a look at a couple of problems. One thing I want you to know is that the word substitute means replace. So we're going to be using those words as we move along in this lesson. So looking at this first system of equations, you can see that one of the equations, that first one, is set equal to y. So anytime you have an equation that's part of a system that is already solved for one of the variables, that is a really good indicator that substitution is a good method to use to solve it. Because watch what I'm going to do. We know that y is equal to 6x minus 6. We know that from our first equation. What I'm going to do is I'm going to essentially substitute that expression, so this over here, I'm going to substitute that in for the y in my second equation. Let me show you what that's going to look like. I'm going to go ahead and write it down. 8x minus 3. And this is where I'm going to replace the y. I'm going to replace it with 6x minus 6. And of course, that's equal to 8. So I took the y in the top equation and what that equaled, and I replaced it in the second equation where I saw a y. What that does is it eliminates all of your y values. So now in this new equation, I only have x values. And when you only have one variable to solve for, go ahead and solve for it. So I'm going to use my equation skills from Unit 2, and I'm going to go ahead and solve this out. I'm going to start by distributing my negative 3 into my equation. Then I'm going to go ahead and combine like terms. And then I'm going to go ahead and balance my equation. And these are all skills that we learned back in Unit 2. So that's going to leave me with negative 10x is equal to negative 10. I'm going to simplify this down. And I can see here that my x is going to be equal to 1. So what that means is that the variable x in this system, that is going to be equal to 1. And it also means that that's the x coordinate in my solution. Now, we're not quite done. We have to think about this. We only have the x coordinate, but remember, a solution to a system, I'm going to write it down here, is an x coordinate and a y coordinate. So we need to go and figure out what the y coordinate is. To do that, I'm going to look back at my two equations and kind of think to myself and say, well, which equation is easier for me to substitute that x value of 1 back into to get out the y? And you're probably thinking, well, the first equation, right? The first equation is definitely easier, although the second equation would work fine. So let me show you what that's going to look like. Now I'm going to take y equals, and I'm going to substitute or replace my x with a 1 because that's what our answer for x was. And then simply go ahead and simplify it down. So if I simplify this down, I get that my y coordinate is 0. And therefore, my solution to my system is the coordinate 1, 0. And that's how you use the substitution method. Now, we already know a lot of the terminology from our last lesson, but the first thing we can think of is, well, this has an answer, right? So this has to be a consistent system. And it also has exactly one solution, which makes it independent. Let's try another one. All right, in this next one, this one looks a little bit different. You can see that looking at my two equations, I don't have an equation that is already solved for one of the variables. But if you look at that first example, couldn't I transfer that or kind of simplify that to get y by itself? Do you see how the y right here is all by itself? Well, think about this. I'm just going to rewrite it here to kind of show you the work that I'm doing. If I subtract 3x from both sides, which is a simple little step, That gives me the equation y equals negative 3x plus 7. And now that equation is solved for y, which puts me in a good position to use the substitution method. Because now what I want to do is I want to substitute that equation into the second equation. And remember, what I want to do is take those that negative 3x plus 7, and I'm going to substitute it in for the y in the second equation. So let's go ahead and write that down. 6x plus 3. Now watch, I'm going to substitute it in for y. Negative 3x plus 7. And then I'm going to set that equal to 15. That eliminated all of my y's by doing that substitution. So now I can just simplify my multi-step equation. Let's go ahead and simplify. I'm going to go ahead and distribute. There we go. Now I'm going to go ahead and combine like terms. And then that leads me to a two-step equation. So now what I can do is just balance the equation. So I'm going to go ahead and balance it. I'm going to subtract 21 from both sides. And that leaves me with negative 3x equals negative 6. And I'm going to go ahead and divide both sides by negative 3. And you can see here that that gives me x is equal to 2. So again, that's just the x coordinate. The solution is going to be an x and a y, but we need to go figure out what the y is. So look back up at the beginning and choose one of your equations. I'm going to go ahead and choose the first equation. You could actually substitute it into any of the three that we have here. Remember, either of these two or the one that we created. Remember, they're exactly the same. But I'm just going to go ahead and choose the first one, and I'm going to substitute it in. So 3 times 2 plus y is equal to 7. I'm just going to go ahead and simplify that down. Simplify it down, and I got y is equal to 1. So there you have an x and a y, and there's your coordinate, which is 2, 1. And 2, 1 is where these two lines intersect each other, and that's the solution to the system. Because it has a solution, it is, of course, consistent, and it is also independent because it has exactly one solution. Okay, so you'll notice the amount of work in this procedure, and that is normal for the substitution method. Now, let me show you some more examples. Let's take a look at this first one. You can see here that we don't have an equation that is solved for a specific variable. So, but my eye kind of caught this one right here. Do you see this? So I could take that and kind of manipulate that equation around so that I can use that. Here's what I mean. I'm going to go ahead and I'm going to leave y on the left-hand side, but I'm going to move negative 5x over to the right-hand side. And I'm going to do that in my head. So that's going to leave me with positive 5x plus 7. Now it leaves me in a good position to substitute. So let's go ahead and substitute it now. I'm going to substitute it into the first equation. So 10x minus 2, and I'm going to substitute it in for y. So I'm going to use parentheses there and set it equal to 4. Let's go ahead and simplify down. 10x minus 10x minus 14 is equal to 4. I'm going to combine like terms. You can see here that 10x minus 10x is actually going to give me 0, and I'm going to be left with negative 14 is equal to 4. We've run into a situation like this before now, haven't we? Where it doesn't work. These two numbers are not equal to each other. When you get a situation like this, that means that you don't have a solution, which means you don't have an intersecting point. So I'm going to go ahead and write no solution. Now, if we remember what that means graphically, that means that these two lines are actually parallel. And if they're parallel, that means, of course, these are inconsistent. So that's kind of how that works. Now, I bet you can guess what this last example is going to look like. I bet this is an infinitely many solution. So let's just go see and see if that's what it is. So in this last example, you can see my second equation I have x plus y. That is really easy to just quickly solve for one of those variables. I'm going to go ahead and solve for x. And I'm just going to go ahead and rewrite the equation like this. X equals negative y plus 4. I just kind of moved it over to the other side. Now, I'm going to plug this new equation into the first equation. Here we go. I'm going to substitute it in for x. Negative 3 times, so I'm going to replace the x with negative y plus 4. And then I'm going to carry down everything else. Now, simplify. I'm going to go ahead and distribute. And I'm going to combine like terms. You can see 3y minus 3y gives me 0 again. And I'm left with negative 12 is equal to negative 12. So when you have a situation like this, when the two numbers equal each other, this might feel like a special case situation, which it is. That means that these two equations are actually the same line. And so that you're not really going to have an x and a y because you have infinitely many answers. So I'm going to indicate this by infinitely many solutions, so IMS. And of course, it does have an answer, so it is consistent, but this time it's dependent because it has many answers. So the big thing to know here is just the difference between what it looks like. This first one, when you have two numbers that do not equal each other. See how these do not equal? That means you have no solution. But if you have two numbers that are the same and your variables have depleted, that means that you have infinitely many solutions to this system. And if you don't believe it, the great news is you can always graph these systems to actually see what they look like visually. Because the first one would be parallel lines, and then the second one here would be two lines right on top of one another. So that's the substitution method in solving a system of equations.